Okay, good morning. So on Thursday, I talked a lot about truncation errors in ocean models. So what I'd like to do today is to take a very specific example and give you a little bit of status of the questions that we are asking ourselves right now. So it's just, so I'd like to thank a contribution from several people, in particular Eddy, Ajayi, who is in the audience here, Alexandra Bozek and Chaba Oshu, who are at Florida State, and Romain Badi, who is at Mercator. So what I'm going to do is take specific configuration of the North Atlantic and look how sensitive they are to some of the numerical choices that we make when we run those simulations. So first, here's a little bit the order of the presentation. First, I'm just going to give a very brief history about something that is close to my heart, which is the Gulf Stream separation and its representation in ocean models. So the impact of resolution, higher order schemes, viscosity, and other numerical choices. So first, modeling the Gulf Stream separation. That's been a long-standing issue for if you take a grid spacing that is less than a quarter, higher than a quarter of a degree. In general, the Gulf Stream does not separate from the coast and stays up and follows the coastlines. When you switch to grid spacing that start to resolve the Rossby radius of deformation, so in the order of 10 kilometers, then you start to have a Gulf Stream that looks realistic. So here is an old pictures. It's actually 1996 that the first Eddy resolving simulation of the North Atlantic started to show a Gulf Stream that resembled, you see just here, detaching from Cape Hatteras in white is the envelope of the observed Gulf Stream. So that was done in 1996, and there was collaboration from Rainer Black, professor at the University of Miami, with computer scientists. So the idea was not necessarily to be as, the main goal was to see how far we could push the resolution of a numerical configuration, and to our surprise, we found something that started to look very much like the observation. So this is reported in a paper by Afonso Paiva, who is a professor in Brazil right now, who was a student at the time as well as John Hargrove, myself, and Rainer Black. This was followed by a couple of years later by work with the POP, which is the Los Alamos ocean models, where they ran at 1/10 of a degree and started to also get a Gulf Stream separation that was that actually separated from the coast, because the standard of the time in the 90s was to run at 30 kilometers, 1/3 of a degree, where you systematically had a Gulf Stream that hugged the coast and a big recirculating gyre here at that location. So that was kind of, so 2000, about 15 to 20 years ago, there was a little bit of a regime shift where people start to realize that resolving the Rossby radius of deformation mattered. This is where we are now. This is a 1/50th of a degree run that I presented last time. You see nice, filaments, eddies, everything, very vivid simulation. So it's you could take some snapshots compared to observations. They start to look a lot alike. So why improvement as you increase the grid spacing to 1/10 of a degree? So there are a couple of things that have been put forward. One is that you start to resolve the Rossby radius of deformation up to about 40, 50 north, and the other one is the flows may start to exceed a critical Reynolds number. What I mean by that is the viscosity that we use at 1/10 of a degree is still quite viscous. If you compare that to a fluid that we know, it's a little bit like honey. I mean, it's really, it moves well, but it's not, still not like water. For a 1 degree model, it's more like concrete that you pour in a foundation. So it's, the viscosity is the equivalent viscosity of those models is still quite viscous. It's also very difficult to identify the specific dynamics that control the Gulf Stream separation as you go into primitive equation models. So there's many theories that have been put together. There's about, probably about 50, and there's a few review papers that you can look at. So what I'm going to talk first is recent work on the impact of horizontal resolution going to 112 to 150th, and that's done by using identical North Atlantic configuration. I'm going to talk briefly about comparison to observation, especially using also power spectra. So this is using the HICOM model. That's 32 layers in the vertical, so a hybrid, and but they are identical, meaning the topography is not changed. We use the same topography at 112 degree, so that's about 6 kilometer. At 125th, 3 kilometer, and at 1.5 kilometer. You just refine the grid there. The closed boundary at the north and south with relaxation to climatology, and the forcing is 3-hourly forcing, but climatological, meaning it's repeated year after year. And the viscosity decreases a function of grid spacing when you go from 112 to 125th, and it kept constant when you go from 125th to 150th. So that's recently published in JPO. It takes a lot of computer time, 500,000 CPU hours per model year for the 150th degree. So there's not that many of those simulations. So here is the global overview for the whole domain. In red, this is where you reach steady state about after 5 years, so 112th degree, and you see the 125th and 150th are about the same level of kinetic energy, given the fact that the viscosity is about the same in both models. So here is, again, the vorticity movie for the 150th compared to the 112. So the main reason for presenting this is to give you an idea of the increase in Eddy activity that you see when you go from 112 to 125th. Okay, so much richer, many scales that are much smaller. And so here's another way of looking at it. This is for a specific snapshot in winter when you have the maximum sub-mesoscale Eddy activity. This is 150th, this is 120. Okay, so very big difference in the amount of a small-scale feature. Then the same thing between summer and winter in the 150th. Julien showed a similar picture for the NEMO model, but that's the results of the Barkling instability in the mixed layer. So here is another movie again, the 150th vorticity, and together with the sea surface. The main reason why I'm showing this is just to realize that if I showed all the sea surface height movies of the 112, 125th, 150th, you would not see that much of a difference visually with your eyes, because it's, you have to do 2 derivatives in order to get the vorticity, and therefore the sea surface height field look pretty smooth. You see some eddies in everywhere, but you don't see all the small scales that are really, truly, you have to derive twice in order to get them. So if you look now, going back to the Gulf Stream and the its separation and penetration, on the left is the latest Aviso mean that Pierre presented. So that's the mean dynamic topography derived from the geoid and observations. So that's a traditional 112. That's pretty much standard state of the art that most centers are running right now. Usually the separation is reasonable, but what you see is you have a small recirculating gyres, and then when you reach a New England seamount, the Gulf Stream is not coherent and start to spread apart. And that's why you see, all the sea surface height contour to diverge a little bit here. When you switch to 125th degree, you get a stronger recirculation, but again, you have a hard time to pass that longitude here, and that's where. And it's only, at least in this case, a particular case of simulation, that when you go to 150th degree and you start to resolve the sub-mesoscale, that you have a mean sea surface height that very closely resembles the observation. So the message, and I'll repeat that in a few minutes, is that as you switch from, going from 1/3 degree to 1/12 degree, when you start to resolve the mesoscale, there's a big difference in the Gulf Stream separation and representation. But it appears that for this set of simulation, once you start to resolve the sub-mesoscale, you switch to another regime. And my hand-waving argument is that the sub-mesoscale allows the inertial gyre to be better represented in this case. So the main thing is, how do you validate? So I'm just going to show a few things to comparison to the observation. Remember, the message that we try to put across is that your numerical model need to be as close as possible to the observations before you do data assimilation. You don't want a bias. And if your model always wants to separate north or south, you're never going to be able to predict the Gulf Stream correctly. So this is work done by Bruce Lunde at NRL, where you have XBTs that have been flown over the Gulf Stream, over this specific altimeter track. So you can compare altimetry to the in situ measurement. Therefore, you can derive the exact mean dynamic topography from this. And that's the one that is in black. And then if you do the same section in the model, you can start to compare to this, as well as the Aviso, which is the one in the dashed line, which is very close to the in situ measured one. So what we're looking for is the steepness. And you see that the 112 and 125s are further away than the 150s is. So that's encouraging. The other thing is now, the other things that you can evaluate is look at the Eddy kinetic energy. I mean the variability in the model. So this is derived from altimetry, Aviso. But one thing you have to keep in mind, this is done on a 1/4 degree grid using 10-day windows, and that like Rosemary mentioned, the altimeter data are heavily filtered at 70 to 150 kilometer. That's the features that are represented. So I'll get back to this in a moment. So if you look at 1/12 degree, you see that the EKE is mostly confined and spread out west of the New England seamounts. There are very strong topographic feature in that area. If you go to 1/25 degree, it's increased. But still, you do not have this nice penetration that you start to see in the 1/50 degree. On the other hand, the biggest difference is that you see that the energy is higher in the 1/50 degree than to the Aviso. So let's get back to this in a second. But first, this is surface information I provided. So we don't have a lot of long time series at depths. But one of them is from the 80s, so that's quite a few years ago. Some moorings were left for several years. Therefore, you at 55 West, which is this section here. And so what happens is that at 1/12 degree, the EKE, the variability of the surface, does not penetrate. There is no communication from the surface layers into the lower layers. Therefore, you don't have a lot of energy at depths. So it's very quiescent. As you go to 1/25, you start to increase the transfer of energy from the surface to the lower layers. And it's only when you get at 1/50 degree that you start to have EKE that are the same level and same representation. So again, this shows that going from 1/12, 1/25 to 1/50 improve the realism of the simulation. So there is a few maps that were done. This is from the 90s. And if you look at the 1/12, so it's hard to see the numbers, but take my word for it, is that when you go to 1/50, that map and the EKE that is based on drifters is the same order of magnitude. You can also use Argo floats. So that's paper by group in Brest, Colin de Verdier, and sorry, name forgot the. So but that's done on a 1 degree grid. So that looks pretty diffuse. That's what you see at 1/50 degree. But if you subsample the EKE of the 1/50 degree on a 1 degree grid with 30-day average, you start to recover the same level of eddy kinetic energy. So that's derived from Argo floats and just the displacement. Okay. So one of the questions you can ask is, why is it that the model in the EKE from the model 1/50 degree is higher than the 1/12 degree? So it's a fact that when you compute the EKE from altimetry, you take the sea surface height anomaly, you derive the geostrophic velocity, and that's how you compute the EKE. You don't use a total velocity. So when you get to 1/50 degree, especially when you have submesoscale features, you have a lot of ageostrophic motion. And or the other aspect is the fact that you're looking at Aviso is on a 1/4 of a degree grid and with a lot of filters applied to it. So this is the surface EKE. You see 1/50 degrees much larger than the Aviso, but if you remove the geostrophic component, it differs. I mean, you remove all the Ekman drift and everything, but it does not really go toward the observations. So what we do for that, we look at power spectra. You've heard them introduced by Julien, Baylor, and Rosemary. I mean, the main thing is you look at the energy cascade toward the large scale and lower scale. If you do this in this 10 by 20 degree box that covers the Gulf Stream, you see that the slope 112, 125th, 150th, they're all pretty much the same, k to the minus 5 in this particular case. So we're going to focus on this and look at what's happening. So this is a 1/50th degree, pretty much straight line, k to the minus 5 slope. And then you do the same thing using the Aviso 1/4 of a degree. This is a black line, and it differs quite a bit from this one. So what we do, we first subsample the 1/50th degree on the 1/4 of degree grid. That's what you see, the green line. So when you start to have no features at 1/4 degree, the spectra drops off. If you do 10-day average, which is pretty much what Aviso is doing, they have a 10-day window, you start to see another drop off. If you do an 150 kilometer bandpass, which is pretty much what Aviso truly resolve, you get the light blue line, and when you combine the 10-day to the 150 kilometer average, you get the purple line, which is pretty much on top of the Aviso product. So and now if you look at Aviso, take the fully 150th, you apply the 150 kilometer bandpass. That's the picture you get. When you apply both, this is what you have, which is much closer to Aviso. So the take-home message here that I'd like you to do, first, there is a significant improvement in Gulf Stream separation pathway at 1/50th degree, at least with this numerical model. I mean, that's been shown also earlier on with simpler models, so it's not necessarily just this model. So it's a possible regime shift. When you start to truly resolve the submesoscale, you have a better representation of that region. And then the level of EKE in that model is very comparable to the observations. So now, many things, this is a numerical model, you still have to question your configuration. And one of them, which is the fact that you use a prescribed atmosphere. This is not coupled. But not only it is a prescribed atmosphere, but also the wind stress, the way we force and push the water at the surface, is computing using atmospheric wind velocity. So we do not take into account the fact that the stress is going to differ if the ocean current, if you have a water moving at the same time. If the water is moving at the same speed as the atmosphere, there's no stress. Okay, so then or vice versa, if the water is moving the opposite direction, you increase the stress. So technically, what you're supposed to do is to take into account what we call the relative wind, or the difference between the velocity of the ocean and the atmosphere. Now, the atmosphere can respond to this, so it's not a perfect parameterization. But when you do that, you decrease EKE by 30%. So pretty happy that our numerical model has the same level of EKE as the observations, but if I'm going to use this relative wind, suddenly the EKE is going to decrease. So that prompted us to say, how do we maintain the level of EKE that we have at 1/50th of a degree? Okay, or how can we increase the EKE by increasing viscosity or increasing the order of the advection scheme? So like talk a little bit about it. We know to some extent on how to increase the level of EKE, but then it also decreases the realism of the simulation. So here we go. So what we've done is to go to a very simple box configuration, and that's steady 2-gyre wind stress. So you have two gyres, western boundary current separating in the middle here. This is very classic idealized box configuration that has been used extensively for the past 40 years. And what we've done, very simple, basic stuff, we reduce, we increase the resolution, 20 kilometer, 10 kilometer, 4, 2, and 1. So this is a stream function. Overall, you retain the 2 gyro configuration, even if it's a little more, some different things. So here's the movie, and that maybe gives you a little better idea of also what's happening. 20 kilometer, you see there's very sluggish. I mean, this is what, it's still, 20 kilometers is a quarter degree. So if, even climate models are at 1 degree, and they're only now that they're starting to reach 1/4 of a degree. Typical 1/10 of a degree, 10 kilometer, 1 kilometer. It's a whole different world. I mean, you have a lot of submesoscale activity, everything. So it's, how relevant those simulations are to the large-scale ocean, it's a little bit, that can be questioned, but that really illustrates the impact of resolution. But now if you look at, so all the simulations, by the way, now I'm going to define Laplacian and barharmonic viscosity, which is a numerical closure. It's not the QG lease that Baylor talked about, but this is traditionally how numerical ocean models are, do their numerical closure. So on the left, Laplacian viscosity, on the right, barharmonic. In blue, green, red, yellow, as you decrease the horizontal resolution. And here's 4/10 to the -4, and I think 4/10 to the -4 is here. So you see that you have a huge increase in the total kinetic energy as you go from barharmonic to, from Laplacian to barharmonic. The fact is, barharmonic is dissipates only the features that are on the 2 delta x, very small scales. So the energy cascade goes really much to the small scale, and you dissipate the numerical. When the Laplacian is much more larger scale, this type of dissipation, much more viscous. The other thing is, what I show is in thick line is a 2nd order advection scheme. The 4th order, in this case, is using the quick scheme. And the point is that as you increase resolution, at 20 kilometers, you don't see much of a difference between 2nd and 4th order. You start to see some, but barely at 10 kilometers. And you see a little bit more as you keep increasing the resolution. But it's truly designed in this particular case to work with barharmonic. And you see that a 2 kilometer is equivalent to a 1 kilometer 2nd order is equivalent to a 1 kilometer 4th order. So just going to a 4th order scheme is going to increase the level of kinetic energy. So that's what we've done, in the past few months. I mean, this is just finished the runs a few days ago. We did a series of 1/12 degree. We have not been able to afford it to go to 1/25, 1/50 yet. But on the top left is a classic 1/12 degree. And what worked for us systematically for the past 20 years was to use a barharmonic plus a combination of a barharmonic and Laplacian. If we just use a barharmonic, usually we get premature separation, eddies that do not dissipate and everything. So what has worked well for us in HICOM has always been to use a barharmonic plus Laplacian. By the way, okay, so that's 2nd order. That's a traditional run. Now if you do the same, just switching to 4th order, what you see is a significant improvement again in the separation. So we're trying to understand what's happening here, but you start to have a much more coherent jet, still separate, at the New England CML starting to spread out. But if you use barharmonic 4th order versus 2nd order, you again see a big difference, but the barharmonic has a tendency to behave more like the 1/25. Too much eddy kinetic energy, not enough coherent feature. So what it means is that the subgrid scale parameterization in this case is not able to, has enough information on the larger scale. So this is just to illustrate how sensitive, and this is the observation that we're trying to match, and you see it's starting to get to 1/12 degree closer. So the level of energy in the system as you go from the second order, this is Laplacian with the second and fourth order, and you just going to bioharmonic, you start to reach a level that we had at 1/50th degree beforehand. If you look at the eddy kinetic energy, this is what we had before, 1/12th degree bioharmonic plus Laplacian. Where you go to bioharmonic, you start to have a lot of eddy kinetic energy everywhere over the domain. But on the other hand, at the 1/12th degree, fourth order bioharmonic plus Laplacian, you start to have, again, a decent agreement in shape in the AKE. So, take-home message for this one is that the large-scale circulation is quite sensitive, still very sensitive to the subweight scale closure choices that we're doing, especially viscosity in this case, still trying to understand, and the order of the advection scheme. So there is a lot to be learned still at this point. To further illustrate this, this is work that Eddy at GIE with Julien Le Sommer are doing. They are comparing the equivalent North Atlantic 1/60th degree done with NEMO to the HICOM 150th degree. There's two differences that I like to point out. One is the number of vertical discretization, 300 levels in the vertical, which is really very fine, and 32 for HICOM. This is isopycnic coordinate layers in the interior, so the water mass are well represented, and there is a lot of layers in the mixed layers, so we surmise that mixed layer physics is reasonably well represented in both models, but that's an open question. Somebody was asking about this last Thursday. But the biggest one, to me, one of the things that matters is the difference in viscosity. They're using just the bioharmonic when we're using the bioharmonic plus Laplacian. So let's have a look at that simulation a little bit. So what Eddy did is to take compute power spectra over those 10 by 10 degree boxes that you see here. And here I'm just going to present a little bit of a subset to give you an idea. So in red is NEMO 1/60th degree, and in black the HICOM 1/50th degree. The main point is that you do not see anything major. They do not read the sea surface heights signature, the slope, the shape. The 1/60th degree is slightly higher resolution than 1/50th, so you see the tail at the end, a little bit some differences. But the main thing is that they look reasonably alike. There's not a big difference in the slope or anything. So you can compute the slope, that's what you see. So here is the slope, the way Rosemary was describing it, for the mesoscale, between 70 and 250. And you see that pretty much in red, between the red and the black, numbers are about the same. And sorry, on the right-hand side, it's the same thing, but more in the 10 to 100 kilometer range. And there is very little difference in the slope. Where there is a difference that we're trying to understand a bit better, is it due to the choice of subweight scale closure or the vertical resolution, is the number of eddies versus their size. And what you have is that in the NEMO, in a TL60, you have a lot more smaller scale eddies, and not that many mesoscales. So it's the tendency for the eddy, the numbers and size, is to be shifted to the left, and more being in 20, 30, 40 kilometer scale, instead of being in the larger scale that you see in the HICOM. My personal interpretation that needs to be, that Eddy is going to look at in more detail, is I think it has to do with the way the scale selection that is done in the subweight scale closure, but that's a question, an open question. But you see it's pretty drastic. I mean, you see a lot of smaller scale eddies versus more mesoscale in the HICOM. Okay, so to conclude, I would like to also show some other sensitivity to no slip versus free slip, so western boundary, lateral boundary conditions, and a little bit to some of the vertical coordinates. And how did we do this? This is, I spent a year on sabbatical in Toulouse, and therefore at Mercator, and what Romain that it did is took the exact same configuration that we configured HICOM for at 1/12 of a degree. So same topography, same forcing, same everything, lateral boundary conditions. So we're trying to have a comparison that allows us to differentiate between the numerics by forgetting about all the other things. So, and what we're looking at is those runs were integrated for 10 years, and we are interested to first order at looking at the drift. How is the temperature and salinity evolving in time, and how does it differ from climatology, which is our reference? So this is at the surface. So surface temperature bias after 10 years of integration, identical NEMO HICOM. And let me emphasize a little bit the western boundary current and separation here. First, if you look at the basic HICOM, which is hybrid coordinate, and the NEMO, pure, which is Z in the slice, is the bias in HICOM is that it's too warm at the surface, and it's a little more distributed here in the NEMO Z. What the Romain did is repeat the simulation by using no-slip boundary conditions. And lo and behold, when you use no-slip, which is a natural boundary conditions, but questionable maybe at that great resolution, you start to see the similar bias occurring. So the solution is sensitive to the choice of lateral boundary conditions. Now, if they went to the sigma z, which is a hybrid in the vertical, layered, and terrain following coordinate, but still free slip, then you have fairly similar behavior to the original one. You can look at the same thing in the interior. So this is the temperature bias at 1,000 meters. And here, you don't see as much in the Gulf Stream region, but now you can start to look at the impact of the MED outflow and how it's represented in the various models. In the case of HICOM, there's not enough entrainment. Remember that you have to parameterize it, so therefore you see a little bit of the cold bias, when in the other one you see a little more of the warm bias, especially north of the Gulf of Cadiz there. But that's reduced when you go to sigma z, and then when you use no slip, it's the location of this warm bias is shifted south. So again, very strong sensitivity to lateral boundary conditions, something that we didn't see in HICOM, so we need to go back and revisit. So we're starting to communicate among various ocean modelers at scales that we have not done before. There's discussion of putting together a framework where you can bring in the dynamical core and the forcing, topography, everything are always identical, so you can really understand model error and where the differences in model can come from. So, because before we call them beauty contest, you try to make them look as close to the observation, but nobody knows what kind of knob you have tweaked, boundary conditions. So that allows us to really start to get an understanding, or at least, an inkling of where the differences are coming from. So I'll stop here and try to finish a bit early so that we have a little bit of time for questions and not being rushed like we were last time. So thank you.
Questions to Eric?
You explained the differences with aviso and high-resolution HICOM modeling is due to resolving better, smaller geostrophic scales and so forth. But what's the reason of differences of sea level anomaly itself, not kinetic energy?
You're asking the difference between sea level?
Yeah, because difference with observations with aviso exists not only in Eddy kinetic energy, but in the level itself. What can cause that?
So what we compared first is what we looked at for the spectra was sea surface height power spectra. So everything was done on sea surface height anomaly. The reason I showed the eddy kinetic energy is the way it's usually computed from sea surface height is using geostrophic velocity. So we want to look a little bit at the, if we could quantify the impact of a geostrophic motion, because we know that sub-mesoscale features are highly non-geostrophic. Okay, that's the reason why I wanted to emphasize a little bit the EKE. Otherwise, all the comparisons were done on sea surface height anomaly. Did I answer your question?
No, the question was about sea level anomaly, not about eddy kinetic energy.
Well, yeah, but what I mentioned is everything that we've done was done on sea surface height. So if you look at this comparison here, the power spectra is sea surface height power spectra. So when you subsample HICOM, you fall back on the observations. But everything is done on sea surface height. The eddy kinetic energy was only used as an illustration to emphasize ageostrophic versus geostrophic effects.
Okay, thank you.
Other question? Maybe I have one, Eric. Is it fair to do that? Because the Avisa is maps resulting OI interpolation comparison.
Right, but that's the idea of what, ideally, in order to be truly accurate, you should subsample the HICOM 150th degree and run it through the OI of that Aviso is running it through. We did that as what I call a poor man's way of doing it, because if you do a 10-day average, it's maybe a little more smoother than you would do through the OI. Same thing for the 150-kilometer bandpass. But it's an illustration of what the OI is doing, and maybe you could do it a little more accurately, but I think it's a fair comparison.
Okay. Other question? Yes.
My question is that when you saw the comparison between that eddy kinetic energy using altimeters and model with 1/12 and high resolutions, so you have regraded the model into altimeter resolution, or you have directly estimated the kinetic energy? Because altimeter is quarter degree resolution and model is higher resolutions.
So in this case, the EK is computed from deriving the geostrophic velocity from the 1/4 of a degree grid.
Yeah, 1/4 of grid, and this is 1/12, or this is?
This is 1/50. This is on the grid. This is a total eddy kinetic energy at 1/50th degree.
So that means you have not regraded 1/50 to 1/4 or that altimeter
Right.
grid.
So here it is. Here's what we've done by doing pretty much regraded on the coarser resolution and also doing 10-day average. And that's what happened. That was the main goal of this exercise, is to emphasize the fact that Aviso gives you an idea of the eddy variability, but it underestimates the actual eddy kinetic energy or the surface height variability.
Okay,
So
yeah, actually...
The message is if you take this as the observations, actually you underestimate the observed variability.
Yeah, that is okay. But my question was that even though we know the limitation of the observations, the ABA showed, because it is 1/4 degree, so usually what we are doing that 1/50 is the model resolution, we regrade into 1/4, then doing the comparison. So it is similar, or you have done this one?
It's similar to the question that Jacques was asking. It's not exactly similar to what Aviso is doing, but we feel like we have done a process that is relevant and more comparable. So we have not, yeah, it's true, we could have reprojected on a 1/4 degree that maybe have even decreased further the comparison. So we kept this on the 1/50, so that's fair enough. Yeah, we can even decrease that a little bit more.
Yeah, John.
Yeah, Eric, you show a nice comparison of the differences between the Laplacian and biharmonic closures, but you didn't say what coefficients you used for those at different resolution, and I wonder if you have, for the students, an objective way of choosing those coefficients, especially when you're mixing the two schemes together.
Right. No objective way, but the way it's done, it's decreased the strengths of the Laplacian and the Baramanic is decreased in a consistent way as you increase resolution. So A2 is what we call a diffusive velocity multiplied by the grid scale. So the diffusive velocity is constant. And you do the same for the Baramanics. Diffusive velocity multiplied by delta x to the cube. So that's if you use a constant Laplacian and Baramanic, the way which is true for the box. In the case of the North Atlantic, it's a little more complicated, so I refer you to the papers we wrote on this, where we actually, the coefficient also has a little bit of Smagoinski in there. So there's no objective way. I mean, when we first tried the Laplacian, I mean, I had slides, I didn't remove them, but we showed that the Gulf Stream was not separating well, just it was purely Laplacian. When we're doing Baramanic like everybody else, we got this eddy, standing eddy there, so it's only when we combine the two that suddenly the pathway popped up. So it's truly knobs. The next step that is to follow up a little bit in the footstep of Baylor and try to see if we can implement the QG lease instead of Smagoinski/this and see if we can improve the represent. So it's ad hoc. It just looks good. But that's why we're trying to quantify a bit better. Thank you, John.
How's the question? By the way, is there a theoretical foundation to just add a Laplacian and a Baramanic like this, or just?
None. I mean, this is numerical closure. And the reason why we use Laplacian is because the Navier-Stokes, the molecular diffusivity is in the form of Laplacian. So they just, eddy viscosity is parameterized through the tensors. You can theoretically provide some kind of justifications, but at least Laplacian has a little bit of, in quote, justification. But Baramanic is pure numerical closure, just so that your numerical model, you dissipate the noise and it doesn't blow up. So.
Okay, thank you, Eric.